Welcome to The Explainer. Today, we're diving into a fascinating and honestly, absolutely crucial engineering science, the joining of metals. Think about it. Whether you're looking at a spacecraft, a bullet train, or even just the device you're watching this on right now, you're looking at materials that have been permanently bound together. But how we actually achieve that bond? Well, that has evolved dramatically. We've gone all the way from the intense, violent heat of traditional fusion welding right through to the incredibly ingenious solid-state mechanics of friction. I am so excited to guide you through this today because the physics behind these everyday structures are just mind-blowing. It really starts with a fundamental question. How do you build complex machines that are just impossible to manufacture in a single piece? I mean, think about a nuclear reactor or an entire aircraft fuselage. You simply cannot cast or machine those massive structures out of one giant block of metal. It's physically and economically impossible. Plus, we need to transport products in pieces and replace worn-out parts over time. So joining isn't just some optional manufacturing step, it is a fundamental necessity of modern civilization. Okay, let's dive into this. Here is our roadmap for today. 1. The need to join metals. 2. Exploring fusion welding. 3. Design and heat variables. 4. The solid-state alternative. And 5. Friction stir welding. Section 1. The need to join metals. So manufacturing complex assemblies means we have to bring various components together. Sometimes they're made of the exact same alloy, and other times we're dealing with completely dissimilar metals. If you look at the entire family of joining processes, it essentially branches out like a massive tree. You've got mechanical fastening and adhesive bonding over on one side, but our primary focus is right there in the center, welding. And notice how that welding tree splits into two totally distinct paths. You have fusion, which covers chemical and electrical methods like arc and laser beams. Then you have solid-state welding, relying on things like friction. Today, we're going to trace the path right from that fusion branch over to the mechanical solid-state branch.
Section 2. Exploring fusion welding.
For decades, when anyone said the word welding, this is exactly what they meant. Fusion is the traditional backbone of heavy industry. But what is it really? Simply put, it's a process that uses intense heat to melt base metals together. Sounds straightforward, right? But the actual physics are remarkably violent. You are pumping in so much shear energy that you're forcing a massive phase transformation. You're literally taking a solid, structural piece of metal, turning it into a boiling, chaotic liquid puddle, and then just waiting for it to solidify again. This thermal shock creates distinct zones: the molten fusion zone, the partially melted zone, and the heat-affected zone. So the base materials are fundamentally and honestly sometimes negatively altered by this intense thermal cycle. To really put this into perspective, let's contrast the two approaches. Picture a classic robotic arc welder. Sparks are flying everywhere. The light is blinding. The metal is literally boiling. It's chaotic and by nature kind of destructive. It's a bit like trying to glue ice cubes together with a blowtorch. Now contrast that with a solid-state tool plunging cleanly into metal without a single spark. Melting versus stirring. It's like stirring heavy dough instead of trying to manage a liquid puddle. It perfectly captures two entirely different philosophies of joining materials. Section 3. Design and heat variables. Because fusion welding relies so heavily on that extreme, violent heat, it requires this incredibly strict engineering balancing act. Welding isn't just sticking things together. Engineers have to obsess over how the heat of a fusion weld will impact yield strength, tensile strength, and ductility. Will the joint survive fatigue? Will it stay tough? Physically, the metal's thermal conductivity and melting temperature dictate exactly how that heat is going to spread. If a metal conducts heat too quickly, it becomes a total nightmare trying to keep the weld pool molten without pumping in ridiculous amounts of energy. And this relationship between heat input and power density brilliantly illustrates the trade-offs we're dealing with. In fusion welding, you've got a whole spectrum of tools. Take gas welding. It has low power density. It spreads a ton of heat over a really wide area, which heavily damages the workpiece by creating a massive heat-affected zone. But as you move down the curve to arc welding, the power density increases and the focus tightens up. Finally, you get to high-energy beams like lasers. They have unbelievably high power density, so they input very little overall heat into the workpiece, which drastically increases weld quality. Though, as you can probably guess, the equipment cost for that skyrockets. Minimizing that heat input is absolutely vital, and the data tells a pretty cautionary tale. Take a look at the steep drop-offs showing the variation of weld strength against heat input. For alloys like 6061 and 7039 aluminum, as the heat input increases, the strength of the final joint just plummets. If a fusion welder inputs too much heat, they literally destroy the mechanical integrity of the metal. It's a delicate thermal dance. One wrong move and you've compromised the entire structure.
Section 4. The solid-state alternative.
So this constant battle against the destructive nature of melting brings us to a major narrative twist in engineering. What if you could securely join metals without ever melting them? Enter solid-state welding. These are processes that produce welds without ever reaching a liquid state. The theory here relies entirely on adhesion. If you can eliminate the natural surface barriers, we're talking oxides, contaminants, microscopic roughness, the natural atomic attraction forces of the two metals will cause them to spontaneously weld together. Yeah, it's a completely wild fact. Clean metal inherently wants to bond to itself. Solid-state welding uses a mix of heat, pressure, and time to overcome those barriers, forcing the atoms so close together that they just natively share electrons. When you contrast these two methods directly, you can practically hear metallurgists sighing with relief. Because fusion welding requires that liquid state, it's plagued by some nasty defects. Gas gets trapped, causing porosity, flux gets trapped, causing slag inclusions, and the metal can literally tear itself apart through solidification cracking as it cools. Solid state? It cleverly sidesteps these nightmares entirely. No melting means those specific defects are physically impossible. There's no need for filler materials, and get this, we can easily join dissimilar metals that would normally reject each other in a liquid melt pool. To ground this science in everyday reality, honestly, just reach into your pocket. The bimetallic US quarter is a perfect example of a solid-state joining process called roll bonding. Two different metals are forced through rigid rollers under immense pressure. That pressure breaks up the surface oxides and creates a permanent atomic bond, without a single drop of liquid metal. Good luck trying to peel George Washington off of that copper core. Section 5. Friction stir welding. Now, roll bonding is fantastic for flat sheets, sure, but modern engineering needed a solid-state solution for complex, thick structural joints. Invented in the UK back in 1991, friction stir welding completely answered this call. The process happens in three main stages, using a non-consumable spinning tool. First, plunging. The spinning tool drives right into the joint line of the two metals. Second, welding by traversing along the seam, physically stirring the solid metal together. And finally, retracting. Once the weld is done, the tool just cleanly pulls away. Now, what's really fascinating here is the tool's geometry. It has two main parts. You've got the wider shoulder on top, and the profiled pin that actually plunges into the metal. This tool serves three absolutely vital functions. First, the friction generates heat, which softens the workpiece, but again, never melts it. Second, the rotating pin moves the plasticized material from front to back, physically stirring those metals together. And third, the tool's shoulder contains the hot softened metal beneath it, forging it under intense pressure. That combo of heat and severe plastic deformation creates incredibly fine, strong grains through a process called dynamic recrystallization. Because we are physically stirring metal with a rotating tool, our whole terminology for the weld changes compared to fusion. We call the two sides of the joint the advancing side and the retreating side. On the advancing side, the tool's rotation direction and its forward travel direction are the same. This means the tool's surface is actively fighting against the natural backward flow of the metal. On the retreating side, the tool's rotation is spinning backwards relative to the travel direction, so it's actually helping to push that metal flow backward. It's this incredibly complex, asymmetrical fluid dynamic happening entirely in a solid state, which is just, wow, awe-inspiring to think about. And here is a statistic that should make every single engineer and environmentalist stop and take notice. Because friction stir welding doesn't require the massive power grid strain and extreme energy spikes needed to literally melt steel or aluminum like fusion arc welders do, it uses only 2 to 5% of the energy consumed by traditional processes. Let that sink in. It is an incredibly environmentally friendly, green technology, and it requires zero external shielding gases or consumable filler wires. And this isn't just some theoretical lab science. It is actively reshaping our world right now. Aerospace agencies quickly adopted this for the cryogenic fuel tanks on space vehicles. The lack of fusion defects is the real hero there. Drastically reduced distortion and zero porosity mean that highly volatile rocket fuel stays exactly where it belongs. And we see the exact same thing with massive, complex components like heat exchanger tube sheets for the nuclear and power generation industries. Keeping radioactive materials safe relies on joint integrity and corrosion resistance that just cannot be compromised by traditional fusion defects. Which leaves us with a pretty provocative thought to wrap up our explainer today. We've seen the delicate, almost precarious thermal balancing acts of traditional fusion welding and all its inherent chaotic defects. And we've seen how solid-state friction completely avoids these pitfalls while using a tiny fraction of the energy. So, as industries demand greener, stronger joints, will the sheer force of stirring eventually replace the intense heat of melting in the factories of tomorrow? It's a massive evolution to witness, and one that fundamentally changes how we build the future. Thank you so much for joining me for this explainer. I hope it sparked your curiosity to go out and learn more.